right, looking at this review on the front page, questions 1 through 8, is there anything that you're unsure of or you feel that we need to review?
1 through 8.
Looking at questions 1 through 8.
Oh, that's not how that's going to be.
I mean, it's going to be questions in regards to this, yes, sir.
So 4, 5, and 6, would that be, it's closer to 7 or stuff like that when you're describing concentration?
Okay, yes, let's look at 5. If we go based on acid-base theory, remember, acid-base theory it all goes back to that one formula, that idea that if I add my pH and my pOH, what does it equal? Do you remember? pH plus pOH equals 14. What is that 14 representing? The pH scale. So if they are offsetting each other in a solution that would be acidic, what would I have more of? Hydrogen ions or hydroxide ions? The hydrogen ions would be greater. Oh, am I on the wrong side?
No, it was me. I was with me.
Would be greater than the hydroxide ions in a solution that's acidic. In a solution that is basic, what would I have more of? Hydroxide ions. And in a solution that is neutral, they're relatively equal. So in terms of concentration of hydrogen ions to hydroxide ions, that's what we're looking at. Any other questions? There was I had a few concerns about how I saw some definitions on the posters. I don't know if you were just like trying to write something down real quick and maybe, I don't know, maybe, but it's very specific. So I want to go back over that. An Arrhenius acid is what? If I put it in water, what ion would it increase? That increases the hydrogen ion concentration. So if I put it in water, it dissociates. The number of hydrogen ion concentration, the hydrogen ions would increase that concentration of hydrogen ions. Therefore, that would be an Arrhenius acid. What is an Arrhenius base?
One that increases hydroxide.
That's right. One that would increase hydroxide ion concentration. Now, why do we have two separate definitions, Bronsted-Lowry and Arrhenius? Because Arrhenius almost says if it doesn't have an OH, it's not a base. And that's not true. We have many substances that act as bases that don't have hydroxide ions in them, but they're still bases. So that's the difference, the real difference, I think, between the two. A Bronsted-Lowry acid is what?
A substance that has hydrogen, or
Not necessarily. A proton donor it donates protons to the solution or to the reaction. And a Bronsted-Lowry base,
proton receiver.
one that accepts protons. And let's go ahead and, are there any questions with the difference between Bronsted Lowry and Arrhenius? No? All right, characteristics of strong acids and bases. I think, didn't I go through that with you? No. Okay, they're all electrolytes, right? Where would a strong acid fall on the pH scale?
Low, 0 to 3 or 4.
A strong acid would be closer to 0 on the scale. And actually, I should just write it down here. So somewhere in the middle is 7, it's neutral. Strong acids are over here. Where would strong bases be?
Closer to 14.
Strong base over here. So where would a weak acid be?
Closer to 0. I mean, closer to 7.
Weak. Weak acid on the left side of the 7, weak base on the right side. They are strong acids and bases have, relatively speaking, complete dissociation. So an example of a strong acid would be HCl. If I put hydrochloric acid in water, what are my 2 ions I end up with? All right, so a strong acid, an example of a strong acid would be HCl. If I put HCl in water, what are my 2 ions?
Hydrogen, chlorine.
Hydrogens and chlorine. The fact that I get 100% dissociation between those two is what identifies a strong acid. An example of a strong base would be sodium hydroxide. Whoa. Now, I realize that we end up not with 100% dissociation, but we do end up with a cation completely dissociated. So the fact that the cation is completely dissociated is what we're going to use to determine a weak acid, a weak base from a strong base. And so what are the 2 ions for the sodium hydroxide? What would I end up with? Sodium and the hydroxide. Oh, an example of a weak base would be like ammonium hydroxide, where the ammonium ion is NH4. The nitrogen is still bonded to the hydrogen, so that would be weak. We don't have 100% dissociation on the cation. Does that make sense? Mm-hmm. A weak acid would be like acetic acid, where I have hydrogen dissociating from the acetate polyatomic. That polyatomic, that carbon still hangs on to those 2 oxygen and hydrogens. Therefore, it is a weak acid. One thing we can say about strong acids and strong bases is that both of them are good conductors. Those charged ions can carry electrons, and that's really important, depending on, where they're being used, whether in mechanically or in the human body, whatever the case is, that becomes a big role. All right, any questions? Any other questions on this side of the sheet? Are we good? All right.